All right, welcome. In this explainer, we're going to chart the entire universe of numbers. I mean, all of them. From the simple numbers used to count your spare change, all the way to concepts that stretch into infinity. We're going to see how they all fit together in one single beautiful system.
Now, that might sound kind of huge, maybe even impossible, but seriously, every single number you can possibly think of belongs on a single, elegant map. So let's explore it together, step by step.
So at the very, very top, the entire world of numbers splits into two fundamental continents, if you will. Any number you can conceive of is either what we call a real number or an imaginary one.
So here's the big difference. Real numbers are basically every point you can find on a number line. You know, positives, negatives, fractions, all of it. Imaginary numbers, on the other hand, well, they were kind of invented to break a fundamental rule of those real numbers.
So meet the foundation of all imaginary numbers, the letter I. Mathematicians just defined I as the square root of -1. Now, why on earth would they do that? Well, because no real number, when you multiply it by itself, can ever give you a negative answer. This simple, absolutely brilliant idea opened up a whole new dimension in math. And hey, when you combine a real number and an imaginary one, you get what's called a complex number, and those are crucial for things like electrical engineering and quantum physics. So they're not just some abstract idea.
Okay, let's zoom back in on the real numbers, the ones we bump into every single day. Even within this familiar world, there's another major split into two very distinct tribes. You've got the rationals and the irrationals. First up, let's talk about rational numbers. The name pretty much gives it away. They can be written as a ratio. Any number that you can express as a fraction of two whole numbers, like 1/2 or even the number 7, which is just 7/1, that's a rational number. They're predictable, they're orderly.
And then you've got their mysterious cousins, the irrational numbers. These are the rebels of the number world. You literally cannot write them as a simple fraction, because when you write them as a decimal, they go on forever and ever with no repeating pattern. They're just infinite and, honestly, beautifully unpredictable.
And you've definitely met some of these guys before. Pi is probably the most famous one. We've calculated its digits out into the trillions, and they still don't show any repeating pattern. I mean, think about that. Trillions of digits, just pure, beautiful chaos. The same thing goes for the square root of 2.
So you might be wondering, are these numbers truly real if we can't even finish writing them down? Well, a super simple drawing proves that they are. If you just draw a square where the sides are 1 unit long, the diagonal line cutting across it is exactly the square root of 2. That triangle exists in the real world, so that number has to exist too.
Okay, so this brings us to a really common point of confusion. If a number's decimal goes on forever and ever, doesn't that just automatically make it irrational? The answer, which might surprise you, is actually no. You see, the crucial difference is the pattern. Take 0.333 repeating forever. Sure, it's infinite, but that super clear repeating pattern means it's a rational number. It's just 1 divided by 3. An irrational number like pi, though, has infinite decimals with 0 pattern. That beautiful randomness is the whole key. All right, let's zoom back into that nice, orderly, rational family. This is where we'll find all the familiar numbers we use for counting and measuring and all that basic stuff. And it turns out there's a really clear hierarchy in here. Think of it kind of like building blocks. We start with the most basic, the natural numbers. 1, 2, 3, the ones you first learn for counting stuff. Then you add the whole concept of 0, and boom, you get the whole numbers. After that, you include all the negative versions of those numbers, and you've built the integers. And here is how it all connects so neatly. Every single one of those groups, the integers, the wholes, and the naturals, they're all just specific types of rational numbers. Why? Well, because any integer, let's say -5, can be written as a fraction. It's just -5/1. See? It all fits together perfectly. And the rational family has even more little subdivisions. We can classify integers as either prime, those are like the fundamental atoms of the number world, only divisible by 1 in themselves, like 7, or composite, which are built from primes and have more factors, like 6. And of course, filling in all the little gaps between these integers are the fractions themselves, just representing parts of a whole. So we have this beautiful, organized map of every number. But what's the point? I mean, how does this abstract system actually connect to our world? Oh, the answer is, it's literally everywhere.
This system is the fundamental language of reality. It's how we handle money, how we measure distances in engineering, how we calculate temperatures in science, and how we build the algorithms that power all of our technology. I mean it. Our modern world could not exist without it.
But this entire, incredibly powerful system is built on one crucial rule. It's a rule that if you break it, the whole structure just collapses into a paradox. And it all revolves around this one number right here.
You cannot divide by 0. It's the one absolute unbreakable rule in arithmetic. And trying to do it doesn't give you some infinitely large number or an imaginary one. It just results in a state we call undefined. It's basically a mathematical error, like asking a question that has no possible answer.
So when it comes right down to it, this map we've explored isn't just some human invention we made up for homework. It's a system that we've discovered, and it really seems to be the fundamental code that describes the entire universe, from the tiniest particles to the biggest galaxies.
And this, of course, brings us to a final, pretty fascinating thought. We have this incredibly complete and elegant system that seems to cover everything. But does it, really? This map describes the numbers that we know, which just leaves us to wonder, what other kinds of mathematical structures are still out there, just waiting for us to discover them?